I imagine you all should be able to see my screen. And
Yep.
I can get started. Okay, so welcome to a beginner's guide to SQL presented by me. My name is Bilal. I work at Cockroach Labs. At Cockroach Labs, we work on CockroachDB, which is a distributed SQL database and by distributed, I mean it can be horizontally scaled. So one common challenge with databases is you cannot really scale them and run a lot of data, a lot of queries on them beyond the size of one computer or one machine, one node. CockroachDB solves that. But why do you need a database? What is it for? That is what all of this presentation is for. And if you do not have much of a background in databases, in SQL, or if you don't know SQL at all, you're at the right place. You're here to learn. So let's get into it. So if you have a bunch of stuff, if you have, data, music, things that you want to store, data is everywhere. How are you going to store it? You're going to be building stuff in this talk, in this hackathon, and you are going to want to store your data in a reliable place, in a place where you can easily retrieve it in the form that you want. That's what databases are for. There are different types of databases. I do not have the time to go over all of the different kinds, but the most common and the most commonly used, as well as the oldest type of databases out there, are relational databases. Relational databases try to put everything in a tabular format, in a table-based format, and tables under databases. And you can have relations between these tables. An example here would be, like, let's say you are building a music service. You have a bunch of songs, but you can have multiple playlists reference the same song. You don't want to create a different entry for each song because one of your users added it to their playlist, right? So in this very, very simple example, you have a song table with song ID, song title, and artist. The song ID is probably going to be unique in the table. It's not going to be repeated. And then you have this other playlist table, which has a song ID that references the song that's in it. Now, this is a very simplistic playlist that only has one song. This is what we would call, in this example, this is something that we would call a one-to-many relation, where one song has many playlists. In practice, you're probably going to have a many-to-many relation in this case, which is a little more complex, where you can have multiple playlists referencing multiple songs with a defined ordering. So that's how you would get like some sort of a music playlist service going. And you can see even with this very simple example, it is super obvious how central and how important a database is for your application. It is the heart of your application. And here's my schmeal on why you should use CockroachDB for that. It is very easy to use and it's very easy to set up, which we will be doing in this presentation. So the language that you would use to query your data in CockroachDB or in a lot of SQL database, in a lot of relational databases, is called Sql. It stands for Structured Query Language. And it is this other way to be able to ask for data and to be able to insert data into a database. So while in English, you would say something like, do you like dogs? You could break that down into its different parts. It's got a verb, it's got an object that you're referencing, and it's got a subject that the question is being asked to. You can kind of also break down a SQL query in a similar way. So here would be a SQL query if you wanted to retrieve the names of all dogs where location equals New York City. So this is an actual SQL query. It's something that we would call a select query. The name of the table that you're getting the value from is called dogs. The column that you're interested in is called name. And the where clause, which is optional, in this case is only selecting for conditions where the location equals New York City. You could omit the where clause and you could have a simpler query that just says select name from dogs, and that would return the names of all the dogs in your dogs table. So the other examples of SQL statements that, other than just the select one that I described earlier, would be create, which could create a database or table, use, which sets the active database. I'm gonna use all of these in the next few slides, so you don't need to memorize these or anything. But the more commonly used ones that you're gonna use for things like, for things that we call CRUD operations, create, read, update, delete, would be the select query, which is to read data from a table like we just did. insert, which is to insert rows into a table, update, which is to update rows in place in a table, and delete, which is to delete rows from a table. Pretty self-explanatory. I do not need to describe these words to you because these are English words. SQL should be at least simpler than most programming languages, which is why you do not need a background in, say, C++ or Python to be able to understand or write SQL. Turns out a lot of people who do this in the industry do not often know Python or C++ or other programming languages. So let's do this in practice. I've been talking a lot about this being more of a demo, so let's get right into it. But since we talked a little bit about dogs, I also wanted to say we have a bunch of dogs in our office. These photos are mostly pre-pandemic, back when we used to go to the office. I actually do not know the names of most of these dogs. The company has grown so much. Though I do know that the dog on the bottom right is the CEO's dog. It's called Carl. Yeah, I will throw a recruiting spiel at the end, but we are hiring. So if you are a later year student at a university, studying computer science or so, and you're interested in these kinds of challenges, check out our careers page. Or if you're a new grad, check out our careers page as well. Okay, with that out of the way, let's dive right into it. So I'm gonna go, and feel free to follow along. I'm gonna go to that website over there, which is cockroach.ch/playground. That should take you to this page, which is our interactive console in the browser that will give you a live live CockroachDB database with a SQL shell on it. So right now it's installing, well, it's kind of like faking this installation, but what it's doing is it's kind of creating this cluster for you. And here we now have a shell that should allow us to run SQL queries. Right, so I'm already in a database that has a bunch of tables populated. So I could do select star from users, and that'll show me the users table. It's a pretty well-populated table. But I'm gonna keep this simple, and I'm not gonna touch this database for now. I'm gonna go back to my slides. I'm gonna create a new database from scratch. Oops, I'm just gonna say, create database. I think I should stop presenting and then do this. If you wanna follow along, if you also wanna be able to copy these, I'm gonna drop a link to this presentation in the chat for this Zoom webinar. So you can also follow along if you want. Okay, with that done, let me create this database. Oops, I don't want to do that. That's not going to work. I'm going to create this database called dogs.crl. CRL stands for Cockroach Labs. I'm going to run this use command, which sets the current database to the database that we just created. So you can see the shell now changes to docs.crl. Now that stands for that this is now my current database. And if I were to do, say, show tables to see all the tables in this database, I see none because this is a database we just created. So let's create a new table. I'm going to explain the syntax. I know this looks a little complex, but what's happening here is I'm creating a new table called dogs that has 4 columns. So the columns are described inside these parentheses. The first column is ID. Its type is UUID. UUID is this way to reference random large ID-like unique strings. Don't worry too much about whether you know UUIDs or not. Just think of them as these unique identifiers that are always unique, that are always randomly generated. They look like long strings. The second column is a name. I don't think I need to describe that. The name is a name. Human, which references the name of the human, and location, which references the location of the dog. So I'm going to create this table, and it ran successfully. Now, if I ran show tables again, I should be able to see this. I see this table being created, but if I select from it, it should be empty. Yes, it is empty because I haven't inserted anything into it yet. But before I insert something into it, let me show you an example of an alter table statement, which lets you do what we call a schema change, which is let's say you created a table, but you wanted to now add a new column called favorite treat in it. And favorite is misspelled. So I'm going to change that spelling before I run it. Some of you might say some other people use that spelling of favorite, but no, that's the wrong spelling anyway. So now I've created this table. or sorry, I've created this table and I've added a new column to it. So now if I were to run that select query again, you should also see this favorite tree column, but there are no rows in the table because we haven't added anything to it. So let's go on. So I'm gonna insert into this docs table one row, and this row has this long, so the part before the values and these parentheses, like ID, name, human, location, that just specifies the name of the columns. And then after the values over here, it's describing each of the columns for the rows, for the one row that I'm adding. I can run this insert statement multiple times to add multiple rows. So the ID column here is this long UUID string. Don't worry about it. It's just a unique string that was generated. The name is Atticus. The human is Adrian, who's one of our coworkers, and the location is New York. So I'm just going to run this, and it said it inserted one row. Perfect. So that worked. Let me just, for interest's sake, let me just add a bunch of other dogs. Carl, Spencer, who's the name of our CEO, who's also in New York. That should just work. Yep. So now if I ran the select statement, now I can see there are two dogs. They have similar looking IDs, but they're slightly different. They're unique. One is Atticus by Adrian, and one is Spencer's Carl. I realized I did not set favorite treat, so it's null for both of those dogs. And now that, let's say, a global pandemic strikes or some unfortunate event that forces us to set location to work from home for all of these dogs that are in New York right now. So that would be an example of an update statement. So in this update statement, this is operating on the table dogs. That's why it's update dogs. Set location equals work from home. So column name equals the new value, where location equals New York. So where all the current rows have their location set to New York, it's going to set those location to work from home. So I'm just going to run this query, and it says it updated 2 rows. So if I run the select statement again, now the location column is all set to work from home. And if I wanted to delete a particular row, I could run the delete command. So delete from table name, which in this case is dogs, where name equals Atticus. So it's going to remove that first row over there. So I'm just going to run this query. You can see how the where clause here looks a little similar to the where clause in the select statement earlier. So like if I were to do like select star from dogs, where, whoops, I need a space there, where human equals Spencer. So it's just going to return the one row where human equals Spencer. So I'm going to run that delete statement again that I was talking about, but I did not run. So in this case, we're going to delete all the rows from dogs where name equals Atticus. So it's going to remove that one, that top row. It deleted one row, and then I'll just run a select star with no where clause to see the whole table. And I see it only has one row remaining. So in this quick example, we were able to do select statements to query data from a table with or without filters. We did an insert to add 2 rows. We did an update to change a column across all rows, and we did deletes. You can see how simple this language is, yet it is very powerful. You can do more complex things. You can insert multiple rows one after the other. And you can also join multiple tables, which is something we're going to do in the next part. But before I get into that, does anyone have any questions about what we've done so far? If you have any issues with using the SQL Playground over here on the link that I showed earlier on, this link over here, now would be the time to bring that up. Either unmute or say something, or drop it in the chat. I see there's a question in the chat from Anthony. Can you insert into a specific column like the treats? So the way you would do that, that's a very good question. So right now we only have this one row remaining. So if you wanted to just update this null over here, the way I would do that is I would do update dogs set favorite treat equals, I don't know, candy where ID equals, and I'm just going to copy this ID. So I specifically only want to change it in this one row. So now if I do the select statement again, I can see the favorite treat is set. So if you wanted to insert into a specific column, that would actually be an update because you're not adding a new row, you are updating an existing row, if that makes sense. If that, okay, sounds like that answered your question. Cool. So if anyone else has any questions, feel free to drop them in the chat or raise your hand / unmute and speak. I'll pause for like a few seconds because it can take some time for questions to simmer. Going once, going twice. Okay, seeing none, we can move on. So that was all these, like we ran all of those queries, the ones that are shown here. But let's say you had a more complex schema. Let's say you had a schema that looks like this. The diagram on the right is something that we would call a UML diagram of schema. Don't worry too much about it, unless, of course, you get asked in a job to do a UML diagram, but I imagine that happens very rarely. But what it is showing is it is showing a bunch of tables. So each of these rectangles is a table, corresponds to a table with the title at the top. The bolded rows below the title are the primary key, which can uniquely identify a single row. So like in the example table of dogs that we were working with just now, the ID column was a primary key because the ID will uniquely identify each column. In some of these cases, you can see there are multiple columns that are necessary to uniquely identify a single row in that table. And then the columns below that line that are in the like bottom part of that rectangle, they're all the other columns in that table. And then the lines that you're seeing, the dotted and the like the solid lines, they're describing relations between these tables. So for example, users, a user can have multiple user promo codes. No, sorry, it's the other way. A user can only use one user no, it's the other. It's how I was describing it originally. A user can have multiple user promo codes. There can be multiple vehicles registered under a single user. A user can take multiple rides, and a vehicle location history corresponds to multiple, there can be multiple vehicle location history entries for a given ride, which would correspond to the path of that ride. This might seem complex, but you can see how each of these relationships between table pairs can be described as many to many, one to many. In a one to many case, one row corresponds to many. On the other side, in a many to many, you could have like one row here corresponding to many on this side, as well as one row here corresponding to many on the other side. Don't worry too much about how you would go about implementing all of these in SQL, how you would design your schema around this. If you are interested in that, go to cockroachlabs.com. Our docs give examples for all of those different kinds of relations and so on. But for our purposes, jumping back into our demo, this schema on the right describes the mover database, which is what I was using earlier. So I'm just gonna go back to mover, use mover. Now this is, if you're particularly eagle-eyed, you might have noticed that the tables over here that were shown earlier, it corresponds exactly to the tables over here on the right. So as part of the next step, we're gonna add a drivers table to this mover database, where you can have, so each driver has to correspond to one user and one vehicle. So a driver is the linking relationship between a user and a vehicle. Now I'm just gonna write up this query, and then I'm just gonna describe it as is at the end because it's gonna be a little long. Create table, drivers, and then the values are gonna be, there's gonna be user. So the users table has ID and city. So there's gonna be user, city, string, not null, user ID, which I believe is a UUID, not null, vehicle ID, UUID, not null. And then the cities for the user and the vehicle must match, but their IDs could be different. Is there anything else that would be valuable to know in the drivers table? Registration plate. unless that's stored with the vehicle. Or let's just say rides taken. Let's just add something. Rides taken, integer. So that's a lot of columns. And the interesting part is I'm going to define a relationship using this thing that we call a primary key constraint. Sorry, foreign key. So constraint, foreign key, users, drivers. This name doesn't really matter. Foreign key of user city, user ID, references, users, city ID. And then constraint, do the same thing for vehicles. I'm going to explain all of this once I finish running this query. Foreign key of user city, vehicle ID, references, vehicle. Is it just called city and ID over there? Yep, it's just called city and ID over there. Perfect. So that should just work. It's complaining about, oh, right, I think I might have missed. Did I miss something? User city, vehicle ID. Oh, that should just work. I think I realized what's happening. We do not need these single quotes around constraint names. Clearly, I haven't written this in a while. But yeah, you only need single quotes around, say, column data. You do not need this around identifiers, which is what they are. Vehicle doesn't exist. Yes, it doesn't exist because it's called vehicles. There we go, that worked. So now we have this drivers table that has the 4 things we were talking about. So I can add an example driver just now. So I'll just select star from vehicles, limit 1, and then I'll get a user as well. Turns out they're both in Amsterdam, so that makes this easy. Insert into drivers, which is the table we just created. User city, user ID, vehicle ID. These are the columns we're adding. Values. And then I'm gonna take the user city, which is Amsterdam, and this is gonna be in single quotes because this is an actual cell. User ID is over here. And then the vehicle ID is over here. Of course, in practice, you're gonna be doing this in code. So you wouldn't really need to copy and paste this by hand. You can have whatever your backend is and do this for you. So now I've added that into the drivers table. So I'm just gonna call select star from drivers. And then I can see I've linked this user to this vehicle in the city. And then I can do clever things like select star from drivers inner join. Actually, let's not talk about joins. That might make it more complex. But if you're getting into like being able to link different tables, there are good examples on our docs. And then I'll go back and explain this create table query that I just ran, the statement. So it's creating a table with 4 columns: user city, user ID, vehicle ID, and rights taken, of types string, UUID, and integer. But then the new part here is these foreign key constraints. What the foreign key constraint is saying is that these 2 columns in my current table need to reference these 2 columns in the other table. So any entry in my table over here, for those columns, it must have a matching column in the other table. And in this case, the other table is the users table, and it must match the column city and ID corresponding to these. It must have a row over there. If it doesn't, then I won't be able to add anything here. And I repeat the same thing for the other table that I'm linking this to, which is the vehicles table. Now you can see how the constraint name is just there as an identifier. It really is not used for anything. So this part doesn't matter too much, but what matters is the columns in your current table and the columns in your destination table. So that is one example of how you would do relations in this relational database. I hope I haven't lost any of you. If you have any questions about foreign keys, now would be a great time to ask. I see the chat is empty, but I'll give you all like a few seconds to ask questions. I know we're nearly out of time. This was the last of the examples. If you want to go ahead and do this on your own, feel free to run the recording and feel free to pull up that playground that is linked back over at cockroach.ch/playground. That'll take you to that shell that I was using. And there you can run all of these commands. But the other thing that you can do is, that's what I'm going to jump into, is the shell that I was using right now. It works pretty well for like playing around with SQL. But if you actually want to use a database for your hack, you probably want a cluster that lasts longer than your browser tab. You probably want a cluster that your app can connect to, and you can run queries and create databases and store them permanently over there. You want something that's reliable. So for that, you can create a free CockroachDB serverless account by going to cockroachlabs.cloud/signup. I'm just going to click this just to show you how the signup page looks like. Just fill all of this, and you don't even need to put in a credit card. I know some of you may not even have a credit card. That's totally okay. This will get you a free forever cluster. It's going to be limited in how much data you can store on it, but I would be very surprised if you run into that limit. If you do, feel free to talk to us, but I'm sure you won't. And check out our Cockroach University's Getting Started courses, which can talk more about how to connect to your Cockroach Cloud serverless account from your Python or Node or Ruby app or whatever you're working on. There are also a lot of examples in our docs that talk about how to connect and how to run sample apps. Like I think some of these sample apps over here correspond to a lot of the other tools that you might be working with. So for example, if you're working with Django, here's an example app, complete with all examples. You can clone over there. That'll show you how you can have a Django app that interfaces with CockroachDB. And if you have any other questions, drop by our sponsor channel on Discord when that pops up and just have a chat with us. Does anyone have any other questions? Oh, one last thing. In pure Steve Jobs fashion, we also have a sponsor prize. So for the best use of CockroachDB, you don't need to use our serverless thing for this. If you're running CockroachDB by yourself, that works too. But the best use of CockroachDB, the team that's just for having the best use of CockroachDB, every team member will win an iPad mini, up to 4 team members. And you'll also be featured in a CockroachDB blog post or a live stream. We do a bunch of Twitch live streams from our engineers, and you could hop on and talk about your hack over there. So enjoy building. Ask any questions you have on Discord or right now. And if there are no questions, I guess I'll see you later this week. Okay, thanks all. Not having questions is either a great thing